All right, so today we've got section 2.3, which is a review of some of the things that you learned about polynomials in Algebra 2. Not all of it. This is really just kind of some of the basics. We will review some more things about polynomials coming up. So I'm using grid paper because we're going to have to draw a graph, and you should be fine if you don't have grid paper, but when I'm using this screencasting thing, it's very, very difficult for me to connect my dots well. So I figured this might help a little bit with that, so that hopefully my graphs don't look too terrible and you'll be able to follow along. So title of this section is Polynomial Functions and Their Graphs. So first thing we should probably talk about is review what a polynomial function is. So in order to be a polynomial function, two things have to be true. One is that they have whole number exponents. So exponent could be 0, 1, 2, 3, so on and so forth. You do not have decimal exponents. You do not have fractional exponents that don't simplify. You don't have variable exponents. So whole number exponents, and then the other qualification is real number coefficients. So everything except i's are real numbers. So as long as all your coefficients don't have an I, it satisfies that condition. So this is how you can tell if it's a polynomial by looking at its equation. When you have the graph of a polynomial, they should make smooth and continuous curves. End behavior. I hope that this was something that was really, really stressed to you by your Algebra 2 teachers. I make my students do what I call the polynomial dance moves. So you really need to know what the arrows on the ends do based on a polynomial's equation. So to kind of summarize end behavior in a little chart, there are 4 different categories that you should have learned. A polynomial's end behavior is based on its degree and its leading coefficient. Now, what I'm putting in this chart is not to be confused with any type of answer. These are just the tricks that I use to help people remember what they should look like. If the degree is even and the leading coefficient is positive, then that means on the ends, both your arrows should go up. So meaning if we're talking dance move wise, it would look like you were doing like the touchdown motion. So both ends are going up. What happens in the middle here changes a lot based on the individual equation. But if the degree is even and the leading coefficient is positive, the very far ends look like this. If the degree is even and the leading coefficient is negative, then that means we've got kind of the opposite going on. On both of the far ends, the arrows are going to go down to negative infinity and not come back up. What happens in the middle varies a lot, but both the ends look like that. If the degree is odd and the leading coefficient is positive, then that means that as you are looking at the graph on your paper, the far right side is going up and the far left side is going down. Last one would be when the degree is odd and the leading coefficient is negative, and it does the opposite of the one before. That means as you're looking at the picture, the left side goes up and the right side goes down. So this should have been a stress point in Algebra 2. Hopefully you know that end behavior, but if you don't, then I have retaught it for you there. You do need to make sure that you know that, and that you know, based on its equation, what end behavior you should have. Something that we talk about only very briefly in Algebra 2 is multiplicity. And in Algebra 2, we never call it multiplicity. So multiplicity of 0 means when you have zeros that occur more than once. So there's multiple of the same 0. If a 0 has an even multiplicity, remember that zeros are the same as the x-coordinates of the x-intercept. So if it has even multiplicity, that means that at that particular 0, the graph does what we call touches. Sometimes this pen is hard to use. It touches the x-axis and turns back around. Meaning it doesn't actually cross the x-axis. It touches it and then turns back around. So we didn't talk about multiplicity as a word in Algebra 2, but you did learn, because it's on the embedded assessment in Unit 3, that when you have a double 0, that this happens. So it's not just double zeros. Double zeros are when a 0 appears twice. When we have higher degree polynomials, you could have a 0 that is repeated 4 times, for instance. So any type of even multiplicity is going to have that same behavior. The graph is going to touch the x-axis and turn back around and go back where it came from. Odd multiplicities, so if you have a 0 that appears only once, 1 is an odd number, so that would count. Or if you have something that appears 3 times, that's also odd multiplicity. In those cases, that means that the graph is going to cross the x-axis. This is something that I have always seen on either the midterm term or the final or both. They like set up this chart, and one of the things that they have you fill in about the polynomial is what are the zeros, what's the multiplicity of that 0, what's the behavior of the graph at that 0, and that comes straight from this. So you solve, you say, oh, it has multiplicity 6. So then that's even, so then you would say the graph touches the x-axis and turns back around. So very important that you know that even multiplicities touch and turn, and that odd cross the axis. Something that you definitely did not learn in Algebra 2, which is really the only thing that we're going to learn that's new in this section, is something called the intermediate value theorem. And this actually will come back up in calculus, kind of in a different way, but you'll use it in calculus for sure. And it's called the intermediate value theorem, which we typically abbreviate IVT. You'll also in calculus have one called the MVT, mean value theorem. So what the intermediate value theorem says is that for a polynomial f, so some random polynomial, if it's true that f of a and f of b have opposite signs, then there is at least one value of C between A and B for which f of C equals 0. So this is a math definition. I know it sounds scary. It sounds very mathy, but let's think about what this means, and maybe I'll draw you a little picture here. Let's say that we have a function and we're picking random x values. So let's say that this right here is where A is, and maybe pretty close to it, but not on it, is some other value B. What this is saying is if the y value associated with A, so let's say that the y value associated with A is here. So if we're going by ones, it's like -1, 2, 3, 4, maybe 4 or 5, because I drew that kind of in the middle. And f of b, meaning the y coordinate when the function has an x value of b, is right here. So when the y value of A and the y value of B have different signs, this y is negative, this y is positive. Of course, it could be the other way around, where A was positive and B is negative. But regardless, if this happens where these y values have opposite signs, because polynomials are smooth and continuous curves, that means I know that in order to connect this continuously, that there has to be some sort of curve going through here, which means that I have to have some value of C in here where the y value is 0. So what this is saying in very mathy terms is that if two y values have opposite signs, then there is at least 1, 0, or one solution, or one x-intercept between their x values. So that's kind of what it says in plain English. All right, so let's actually do our examples here then. So first one doesn't have a ton of math work to do. So first example, sorry, sometimes this handwriting doesn't work really well on the screen, but since I have fairly neat handwriting, I feel like it's still okay. So determine if f of x equals x times x minus 7 squared is a, whoa, that definitely didn't work out real well, polynomial. If so, determine, I don't know if it's my sleeve that's getting in the way or what the problem is. It's not normally this hard to use. Determine its end behavior. Okay. So, first thing that we need to look at is we need to decide if it meets the qualifications for being a polynomial. So if I scroll back up to my definition, polynomial functions have whole number exponents and real number coefficients. Well, if you can determine that from the format you've got, awesome. If you can't, then you may want to multiply it out. So x minus 7 squared, I'm still going to leave that x out in front right now. So remember, this needs FOILed. There were at least one or two of you on the last quiz who squared the front and squared the back and left it that way. X minus 7 squared is x squared minus 14x plus 49. So then when I distribute the x, I get x cubed minus 14x squared plus 49x. So all my exponents have to be whole numbers. Here are the exponents: a 3, a 2, a 1, even though it's not written. So yes, they're all whole numbers. Coefficients have to be real numbers. I don't have any i's in my coefficients. So yes, this is a polynomial function. Determine its end behavior. So when I look at this, I see that its degree is odd because degree is the highest exponent that appears, remember. So this is degree 3. Its leading coefficient is a 1, which is positive. So odd degree, positive leading coefficient means that our chart tells us our end behavior looks like this. Do not try to make that your answer. I said when I did the chart that that's not the answer. That gives us kind of a visual picture of what the answer should look like. When you write end behavior, you write it in what's called arrow notation. You did this in Algebra 2. The left sides always start out the same. As x approaches negative infinity, f of x approaches something. We're going to leave that blank right now. And then as x approaches infinity, f of x approaches something. So this part is always the same. You always write as x approaches negative infinity, f of x approaches. As x approaches infinity, f of x approaches. This picture helps us fill out what goes here because it's either an infinity or a negative infinity. As x approaches negative infinity is the left side of the graph. On this picture, the left arrow is pointing down, so that means it's negative infinity. As x approaches infinity means on the right side of the graph. Right side in this case, arrow is pointing up, so that would be positive infinity. So your two answers here are yes and this guy. That is the end behavior in arrow notation. Okay. Hopefully that looks familiar. Now we're going to look at example 2. All right, so for f of x equals negative x to the 4th plus 16x squared. Sorry, that doesn't look like a squared. We are going to find the following. First, end behavior, just like we did on the last one. Second, we are going to find the x-intercepts or zeros with their multiplicity and behavior. C, we are going to find the y-intercept. D, we're going to state any symmetry. So remember that you could have symmetry over the x-axis, the y-axis, or the origin. And then we're going to, most importantly, create an accurate graph. I'm sorry, I don't know why this pen, it does not normally look this sloppy. I might type if this doesn't get much better. So, some of this we really don't need to do work for. Some of this is going to just be look at it and write the answer. So part A, end behavior, that's definitely a look at it kind of thing. When I have my end behavior, I look at the degree, which is 4, degree 4, and my leading coefficient, which is -1. So that's an even degree with a negative leading coefficient. When I look at my chart, even degree negative coefficient means both sides should go down. So that means that as x approaches -infinity, f of x approaches -infinity. And then underneath, you write the same thing, only for as x approaches infinity. Now, the reason why I said you can write the same thing is because I'm not actually going to do it that way. If you didn't learn the shortcut for even degree, because they both approach the same thing, instead of writing it twice, you could just put as x approaches both positive and negative infinity, f of x approaches infinity. As I've said with previous shortcuts, if that just confuses you and you'd rather write both lines every single time, that's fine. Go right on ahead. I'm not going to mark it wrong. So this is my end behavior. Part B asked me for the x-intercepts with their multiplicities and behaviors. So x-intercepts, remember, we find by solving the equation when y is 0. So this is going to be work. 0 equals negative x to the 4th plus 16x squared. So this is a factorable polynomial. There's a GCF of negative x squared, because remember, you always want your front term in the parenthesis to have a positive here. So that then becomes x squared minus 16 inside the parentheses. So I have 0 equals negative x squared. X squared minus 16 is x plus 4 times x minus 4. So when I solve this, negative x squared equals 0, which means x squared equals 0, which means x equals plus or minus 0. Now, positive and negative 0 are the same thing. So this is a double root. I've gotten that answer of 0 twice. This guy, I get x equals -4 and x equals 4. Those both just only occur once. So when I am stating the multiplicity and behavior, I would say that 0, I'm just going to write it up here, 0 has multiplicity 2, which means that it touches the axis and turns. -4 has multiplicity 1. I only got that answer one time, which means that it crosses the axis. And then +4 also has multiplicity 1, also crosses the axis. So I found all of those values. If it because sometimes it says zeros and sometimes it says x-intercept. Sometimes it might have both, like it might ask you for both the zeros and the x-intercept. So remember, the only difference is you would have ordered pairs. So you'd have 0, 0, negative 4, 0, 4, 0, if that's the case. Part C asks you for the y-intercept. That one should always be easy because it's always the constant in standard form. And since there was no constant here, I don't have a plain number, I just have a quadratic and a quartic term, that means that the constant was 0. So 0, 0, the origin is the y-intercept. Symmetry, you might want to wait until after you create the accurate graph, but that's up to you. So here, when I go to graph it, I would definitely enlist the help of your graphing calculator to get you some extra points, because otherwise it's hard to get it accurate. So here, draw one axis, and let's see. Oh no, that's still not good. This is why I tried to use the grid paper, but it's really hard to draw those horizontal lines with this thing. So if I graph this on my graphing calculator, a standard window does not even come close to fitting it. You should know the general shape of this graph because you know the end behavior, and since this is a negative leading coefficient, you know it points down. But the highest value, if you kind of trace around to the max values that you see, or maybe even press second graph and look at the table, you see x's that are above 60. So I'm not going to count by ones on my y-axis. I'm probably going to count by 10s or by 20s. So let's see if I make this 10, 20, 30, 40, 50, 60. Okay, it'll kind of fit. So I'm going to make that 10 just because one little box is way too small for me to be able to hit with this pen. And then I'm going to count by, I'm going to make this like a 1. So I guess I won't label it because if I don't label it, then it's understood to be counting by ones. So here's my y-axis. I know I've got a y-intercept at 0, 0. I also know that I have intercepts at 4, 0 and negative 4, 0. So that's here and here. 1, 2, 3, 4. I know that my end behavior goes down on both far ends, so that means after the last zeros needs to go down. Because the negative 4 and the 4 are both multiplicity 1, we know that it crosses, meaning this is going to continue here. However, at 0, 0, because that was multiplicity 2, you know you're going to have a relative min there because it's going to touch and turn. So now we just need to fill in the middle. And again, I would suggest using the table in your graphing calculator there. If you look at the value when, and I don't have the graphing calculator in front of me, I do have the graph that I drew earlier. It looks like that at negative 1, it's maybe about 15-ish. So I can plot 1 there. Same thing on the positive 1 because we've got that symmetry. And then it looks like at perhaps at negative 2, it's a little less than 50. So 10, 20, 30, 40, 50. So negative 2 and positive 2, a little less than 50. And then at negative 3, we end up with the like 65. So it's just above 60 something right up here. So then we just connect it. Try not to make it pointy. Try to make it appear like a smooth, continuous curve. And I did pretty good for using this thing. And this is our accurate graph. Now, I always get people who forget to go back and then do the symmetry. I think it's a lot easier to do the symmetry once we've looked at the graph, but if you're going to forget, then that's fine. D is the symmetry. This one has symmetry over the y-axis. And then this was part E, our accurate graph. Okay. Last one that I'm going to do here, and I am not going to be able to squish it in this, so I'm going to start it on a new paper here. Hold on one second. I'm done graphing, so I'm not going to use graph paper on this one. So example 3, use the intermediate value theorem to show that f of x equals x cubed minus x minus 1 has a real 0 between 1 and 2. So again, intermediate value theorem says if the y's have opposite signs, there has to be a real 0 between those x's. So first thing we have to do is actually find the y's. So these are the x's. So I need to find f of 1. So 1 cubed is 1, minus 1 is 0, minus 1 again is negative 1. F of 2, 2 cubed minus 2 minus 1, 8. Minus 2 is 6, minus 1 is 5. So f of 1 is negative, f of 2 is positive. So we write out, since f of 1 and f of 2 have opposite signs, there must be a real 0, meaning it has to cross the axis between 1 and 2. All right. I think that's about it. It should cover what you need for your homework. And remember that you can check with the keys for that.